do another example with a long wire. So we have a very long wire. So we're going to assume it goes really far in either direction. Again, this is like engineering infinity. It's not really an infinitely long wire. This is just so far away that if we're out here some distance here, the ends are so far away they don't really do much, because the electric field from one end is this way, the electric field from the other end is that way. Pretty much anywhere you are here, you're going to have electric field left and right, so the left and right components cancel and only the components away from the wire matter. But if you're really far away, then there's almost no Y component, and so we can ignore those effects. So we're assuming that as far as we're concerned, infinite just means that the ends of the wire are much, much farther away than the distance from the wire. Okay. So we're going to have a wire. It's going to have some charge on it, lambda, charge per length. And here we are, and we're some distance, I'm going to call it capital R, away from the wire. And so we got some little dq right here, and that's producing some dE right there. It's balanced by a dq on this side that's the same size dq, making the same dE. Okay, and so only the vertical components matter. Okay. So all we need to do to find the total electric field is we just have to integrate the DEYs. Okay, and then it's going to be in the Y direction. Okay, the way I've drawn it. Okay, so what we want to do is we want to figure out then, okay, so the DEYs are going to be equal to, so the DEY is going to be the DE times an angle. Okay, so what angle? Or this trig function of some angle. So we just want that component right there. Okay. And so we look at that and we say, well, we need that component right there. So we've got right here, we've got an angle theta. Okay. And so we want that theta to, so we would just want the vertical component. So that means this is going to be sine of theta. Okay. So what is sine of theta going to be? Well, sine of theta is going to be how far we are away divided by r, which is the actual distance from the dq to the point that we're interested in. Okay, so the next question is, well, what is r? Well, if we put our origin right here, then this is the x-axis, so that's going to be minus x, that's going to be x this way, so r is going to be the square root of x squared plus r squared. Okay, so we could then say that sine theta is going to be r over square root of x squared plus r squared. And so that means that dE, which is going to be equal to k sub b dq over r squared. Okay. And then dEy is k dq over r squared sine theta. So that's going to be k sub b dq r over, well, that was r, so we're going to have r cubed down here. So the dEy is going to be k sub b r dq over x squared plus r squared to the 3/2. Okay. Now what is dq? Well, if that's lambda, then this little dq is going to be lambda dx. So the dEy is now going to be K sub E R lambda dx over x squared plus r squared to the 3/2. Okay, so now to get E, that's going to be the integral of the dEy from minus infinity to infinity. So that's going to be integral from minus infinity to infinity of K sub E R lambda dx divided by x squared plus r squared to the 3/2. So that comes out to be equal to K sub E R integral times lambda integral from minus infinity to infinity of dx over x squared plus r squared to the 3/2. Okay, and so now we just need to solve that integral. Well, how do we solve that integral? Okay, so in calculus, there's lots of different ways that you have for solving integrals. On the other hand, once you get past the calculus class, there's another way they solve integrals they don't teach you. They teach you integration by trig substitution, integration by parts, integration by this, that, and the other. There's also integration by looking in the back of the book. Okay, so integration by looking in an integral table. So if you look at an integral table, you see that integral dx over x squared plus a squared to the 3/2 is equal to x divided by a squared square root of a squared plus x squared. Okay, so it's like, oh, wow, okay, so that's what you read up in the back of the book as to an integral, and that is pretty much what we got up here. Okay, and so it's like, well, cool, okay, it's just that the a here is going to be the r, okay, and so that means that we can just write down that E is going to be K sub E r lambda, okay, and it's now going to be x over r squared square root of r squared plus x squared, okay, evaluate minus infinity and infinity. Well, right away, that r cancels one of those r's. Okay, and so you look at it and say, okay, so E is going to be K sub E lambda over r times x over square root of r squared plus x squared evaluated at minus infinity and infinity. So what is that? Okay, well, we got to do a limit. Okay, we got infinities in here. So this is like a L'Hopital type thing. Well, actually, it's a little simpler than that. It's like, remember, what does infinity mean? It means huge. So look at square root of r squared plus x squared. If you evaluate that, take the limit as x goes to infinity, what do you get? Well, that means that x is going to be huge. X is vastly bigger than r. So x squared plus r squared is pretty close to x squared, which means the square root is just x. Well, if the numerator is x and the denominator is x, that means the whole thing is 1. Okay, and so that means this comes out to be 1 minus, well, at minus infinity, it's minus 1. Okay, and so that means that the electric field here is going to be 2 K sub E times lambda over r. Okay, or another way of writing that is lambda over 2 pi epsilon naught r. Okay, if you want to put this into vector notation, you can just put r hat. So that would say that for the wire, the electric field points straight away from the wire. The magnitude of it depends on how far r you are from the wire. Okay, and so that there we have an expression for the electric field due to a wire, a long wire. Okay, as long as you know the charge per length on the wire, then you can find the electric field on the wire.